Welcome back. In our last video, we began the process of evaluating a particular integral across or along different paths. First part was along a parabola y squared equal to x, which we did in the previous video. If you have not looked at that, please take a pause to watch that first video. This time around, we want to evaluate I, which is the integral along the straight line 1, 1, 2, 4, 2. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos. Now, do not forget that the integral I, of course, was the integral along this coordinates x plus y to y plus y minus x dx. And so this is dx, and then the other one is the y. Right? This is the integral we have been working with from our last video. Now, we are evaluating along a straight line this time around. So the very first thing is let us generate the equation of the straight line. With coordinate points 1, 1 and 4, 2, we can generate the equation of the line using the 2-point form to generate. So in this case, you could have the equation of the straight line as y minus 1 divided by x minus 1 equals 2 minus 1 divided by 4 minus 1. So in this case, of course, this would simplify into y minus 1 divided by x minus 1 equals 1 divided by 3. 1 divided by 3, of course, being the gradient. So if you cross multiply, you would have 3 into y minus 1 equals x minus 1. This would mean that 3y minus 3 equals x minus 1. So if we decide to reduce the risks of fractions, we could evaluate this as 3y minus 2 equals x. And this would, of course, be the equation of the line. If you want to write it as y equals mx plus c, then you put everything and make y sort of the formula. That also works brilliantly. But I prefer to write it like this. So our substitution will be whole number forms. As always, writing like this would mean that I am making my entire integral in terms of y. Of course, from here, I can differentiate both sides to see that 3 dy equals dx. So now I have a substitution for dx as well. Now if I put that all together, then because my integral will reduce to the times of y, I will have the integral from 1 to 2 still, right? And then wherever I see x, I'll replace it with 3y minus 2, then plus y dx, of course, is replaced by 3 dy, plus y minus 3y minus 2 to y. This is what I'm going to have. Now, I can simplify this a lot further. I have integral from 1 to 2, as always. And then I can write this as 4y. 3y plus y is 4y times 3. That gives me 12y minus 6. And then on this side, I'm going to have minus 2y plus 2 dy. This is what I'm going to have. So in this case, I will become the integral from 1 to 2 of 10y minus 4y. So evaluating this integral, we would have 5y squared minus 4y to evaluate from 1 to 2. So in this regard, what would we have? We would have this immediately reduced to upper bound. 2 is about 2, that's 4, that's 20 minus 8, and then lower bound, that's going to be 5 minus 4. So this is going to be 12 minus 1. So the integral in this case equates into 11. So when we evaluate the integral along the straight line joining the start coordinate 1, 1 to the end coordinate 4, 2, the integral is simply 11. The integral is simply 11. So this, of course, shows us the process of evaluating along a single straight line for the integral. So now the question now arises, what happens when we break the path, which is the third instance? What happens when we break the evaluation into two different straight lines, two connecting straight lines? So instead of taking the journey all at once, what happens when we break this into two? So that leads us into the third part where we take the straight line from 1, 1 to 1, 2, and then from 1, 2 to 2, 4, to 4, 2. So this is what we're going to be looking at next. As always, be sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos.